Recap of Zio Limited case study. Dear participants, hello and a very warm welcome to all of you. Let us recap the Zio Limited case study. An auto parts manufacturing company, Zio Limited, conducts a regular training and development program for its 1,000 employees. It wants to check the current level of satisfaction of employees and that after the training program. You are the chief data scientist in the consultant firm engaged by Zio Limited. The firm has given you the primary survey data response feedback taken from these 1,000 employees pre and post training program and wants you to examine the impact of training program on the employee satisfaction. You have already analyzed the data by summarizing and visualizing it. You have computed various inferential statistics. For example, these included measures of central tendency, for example, median, mode, and mean, measures of variability, for example, range, variance, standard deviation, and mean absolute deviation. You extracted samples from the original data using various probability sampling techniques such as simple random sampling, systematic sampling, stratified sampling, and cluster sampling. You analyze these samples with all the analytical tools learned in the inferential statistics module. You also performed interval estimation techniques using normal distribution and t-distribution to generate confidence intervals. Lastly, you defined detractors having satisfaction levels of less than 4.5 and assigned a score of 0, and promoters with satisfaction level of more than 4.5 and assigned a score of 1. You modeled the data using binomial distribution and made inferences about the population using samples from this detractor promoter data. In this module on hypothesis testing, we'll discuss the implementation of various aspects related to hypothesis testing. First, we'll start by extracting a sample of 50 observations from pre and post variables. We'll start with a simple case of single sample hypothesis test design. First, we'll consider a case where population variance is known. In this case, we'll conduct the hypothesis testing using Z statistics with the assumption of normal distribution. We'll make inferences about the population using our 50 observation sample, employing critical value analysis and p-value analysis. We'll design two-tailed tests to check whether the population mean is same as the desired satisfaction level of 4.5 or is it different. The null hypothesis here is that population mean is same as 4.5. Alternate hypothesis is that population mean is different from 4.5. In the next step, we'll design one tail test to exactly identify whether population mean is more or less than 4.5. In the next set of tests, we'll repeat all the previous analysis, assuming that population variance is not known. So we'll employ t-statistics and students t-distribution to perform hypothesis testing. We'll also examine the impact of sample size on hypothesis testing and analysis with Z and t statistics, and contrast the application of the two distributions, namely normal distribution and students t-distribution. We'll repeat all this analysis for pre and post samples to make inferences about the impact of training and development program on employee satisfaction. Using the original data comprising 1,000 observations, we'll verify whether the inferences made using sample do apply on the actual population parameters. After examining the pre and post samples separately, we'll now examine them together through the application of two sample tests. We'll directly compare the employee satisfaction levels between pre and post sample data and make inferences about the population parameters. We'll conduct the hypothesis using Z and t test statistics. We'll examine whether the means of pre and post sample data are significantly different and can be used for making statistically significant inferences about the population using these results. Finally, we'll convert our survey response data into binary data that is in the form of 0 and 1 of promoters and detractors as we did in the first module. Those with a score of less than 4.5 are considered as detractors and assigned a value of 0. Those that are considered as promoters are assigned a value of 1 who have a score of more than 4.5. We'll model this data using binomial distribution and repeat all the one sample and two sample tests to make inferences about population parameters using the sample. That is, we'll try to examine whether the promoters and detractors have equal probability of appearing in pre and post samples. If not, then we'll examine whether there is a statistically significant impact of training and development program on the proportion of promoters and detractors on the pre and post data. In this module on hypothesis testing, we'll start with downloading the data and generating random samples with 50 observations. In between, some of us may have changed the working directory. However, if we followed our earlier best practice of setting the working directory correctly at the beginning itself, we can straight away run the setwd command and set our working directory wherever our data and other material is stored. So I can straight away run this setwd command, and running this setwd command will set my working directory where all my data is stored. So first we need to read the data. Remember, our data is stored at this location and I simply need to run this read.csv file without giving any location, simply because our working directory is already appropriately set. I can run this data.csv, read.csv, data.csv file, and I can easily read it. Now, as a first step, I need to generate sample with 50 observations. As we recollect, we have generated the samples with a very simple sample command specifying the original population, which is data $pre, and telling R that we need to generate a sample of 50 observations with replacement. So I'm putting the replacement argument as true, which means that all the observations are sampled with replacement. Similarly, I can generate my post sample of 50 observations with the sample command. I can use data $pre 50 observations with replacement. So observations are replaced back into the sample, into population when the sampling is done. So now that we have generated our pre and post samples of 50 length, we will start with the hypothesis testing. And as a starting point, we'll start our hypothesis testing implementation with single population. As a first step in hypothesis testing, we state the null and alternate hypothesis. The framework of hypothesis testing requires us to specify two mutually exclusive hypotheses, that is null hypothesis, often referred to as H0, and alternative hypothesis, which is often referred to as H1. More specifically, we should choose H0 or null to be the case of no effect, that is sample statistic is same as population statistic, or there is no change. Or you can reject H0 and choose H1 to be the case when you want to show or prove something, that is the sample statistic is different from the population statistic. Now, the business case for this may be as follows. Zio Limited, as we discussed earlier, is interested in individuals with a satisfaction of less than 4.5. So those individuals with a satisfaction score of less than 4.5 can be further targeted through training and development programs to improve their satisfaction level. This means that in this case, we want to test the hypothesis whether population mean is same as 4.5 or different from 4.5. That means your null would be that mean is equal to 4.5, and alternate hypothesis is it is not equal to 4.5. And therefore, it is a two-tailed hypothesis. Please also remember, as a convention, we tend to say that we are rejecting the null rather than saying that we are accepting the alternate hypothesis. Here, we'll also examine whether this mean is less than 4.5 or more than 4.5 by conducting single tail tests. And we'll start this hypothesis testing by installing the relevant package, which is BSDA. Once you install this package, you also add this to your current working library with library BSDA command. This will add all the features and functionalities into your current working library, and you can run this. Now, as a starting point, we will run this z.test command to conduct the hypothesis, assuming that variance of the population is known. The syntax is quite easy. We provide the sample, which is pre first. Later on, we will also examine the post sample. Then we'll provide the hypothesized mean, which is 4.5. And then we also state the alternative hypothesis, which is two-sided case. So we are putting as two-sided. That is, it mean can be either less or more as well. We also state the confidence level, which is 0.95 we are putting. That means the significance level is 1 minus 0.95, which is 0.05. Interestingly, we also need to specify the population standard deviation. For population standard deviation, we'll use the standard deviation of original data pre-sample variable, which is pre-variable, as ST. Using ST command, we can compute the standard deviation of original pre-variable. Running this z.test will provide us with the hypothesis testing results. So for example, if I run this, my z statistic is computed as minus 5.5838. Now, if I am going ahead with the critical value method, I need to compute the critical value. So for that, I will run this qnorm command, which will provide me with the appropriate statistic using standard normal distribution. And for that, I need to provide the appropriate p-value, which is 0.05 by 2. Why I'm using 0.05 by 2? Because it is a two-tailed test. So 2.5% significance level on both the tests. Also, please notice that this z value is negative. Even though we are testing two-sided test, but it indicates that the mean is much lower than 4.5. It is on the lower side, considerably lower side. And therefore, it would be more appropriate to put this lower dot tail argument as true. That means we are generating the critical value on the negative side, that is corresponding to the lower tail of 2.5%. And if we run this command, the lower tail statistic is computed as minus 1.96, which is much lower than our z statistic, which clearly indicates that we can reject the null that our population mean is 4.5. This result we could have directly obtained by observing this p-value, which is very small, very small as compared to 2.5%. That means even just by looking at this p-value, which is very significant, we can easily reject the null that our population mean is 4.5. Now that we have understood the basic hypothesis testing using normal distribution, that is z-test, we will further discuss in the next video about hypothesis testing with t-test as well. In the previous video, we discussed how to conduct hypothesis testing with critical value method and p-value method. We conducted a two-tailed hypothesis to check if the population mean was equal to 4.5. Indeed, from our hypothesis testing method, we found that the mean was different from 4.5, and there was some indication that it was less than 4.5. In fact, we could have easily verified our results by running this mean command on our original pre-variable, which is data $pre, to see that the population mean is 4.00, which indicates that our inference from the hypothesis testing that mean is not equal to 4.5 was indeed efficient. Also notice that we chose a significance level of 5%. That means a type 1 error probability of 5%. That is 5% chance that we can reject the null incorrectly. Also notice that z value was negative. If you remember, the z value that we computed was minus 5.58, indicating that pre-sample mean may be much less than 4.5, which is also confirmed by the mean value of data $pre, original data pre-variable here. However, still we would need to test in a more formal manner using single-tailed hypothesis testing, whether the mean is more or less than 4.5. So using our sample, we'll test that as well. And for that, we can design our hypothesis testing procedure like this. So we can use our single tail hypothesis design, and for this we'll again use the similar command, which is z.test, specify the pre, will specify the mean as 4.5, but now notice that I am giving the alternative argument as greater. That means I want to check whether my mean is greater than 4.5 Although we already know that it is less, much less in fact than 4.5, but still we'll check that. We'll put a confidence level as 95%. That means a significance level of 1 minus 0.95 or 5%. Again, since it's a normal distribution based hypothesis testing, that is Z statistic is used, we need to specify our standard deviation from the population. And we are good to run this command. Notice that it gives a p-value of 1, which indicates obviously that this hypothesis testing was largely spurious or not so valid, because the value was much less than 4.5. So even without conducting this hypothesis test, we could have inferred that the mean is less than 4.5, which is also confirmed by the result of this hypothesis testing, that we cannot reject the null that our population mean is greater than 4.5. So we'll move to the second step, where we'll test whether the population mean is less than 4.5. And for that, again, we'll use the sample pre, mu value of 4.5. But in this case, we'll run our alternative as less, which means we are testing whether our population mean is less than 4.5. And we'll use our confidence level again as 0.95. And we'll specify the population variance also as standard deviation of original pre-data. Now if I run this, please notice again my Z value is minus 5.5838. If I want to test my hypothesis using critical value, I can simply compute my critical value as we did earlier with qnorm command. But in this case, I would specify my p-value or significance level as 5%, not 5 by 2, because it is a single tail hypothesis. So I'll put p equal to 0.05. Again, we already know that we are testing for whether mean is less than 4.5. We'll use lower dot tail as true. So we'll get a negative Z statistic. And the statistic here is minus 1.64, which is much less as compared to this Z value, which clearly indicates that we can reject the null and say that true mean is indeed less than 4.5. So we will reject the null, or in other words, we can also say that we will accept the alternative. And now that we have rejected the null, we can say that the mean is less than 4.5 with 95% confidence or 5% significance level. Second point, we could have easily inferred the same by just looking at the p-value. P-value is so small, it is almost close to 0, indicating that with a lot of significance we can reject the null and state that mean is much less than and 4.5, and the result is statistically very significant. Again, you can see that data $pre we will again show it is 4.007. So with 95% confidence, we can say that our hypothesis is correct and the mean is less than 9.5. We can reject the null. Again, there is a 5% chance that we may incorrectly reject the null when it is actually true. However, we can conclude our hypothesis testing here with normal distribution using Z statistic. In subsequent videos, we'll implement the hypothesis testing using students t distribution and t statistic. In the previous video, we have understood how to conduct hypothesis testing using Z statistic when the assumption of normal distribution was valid, and we also knew the population standard deviation. In this video, we'll conduct the hypothesis testing with t statistic. That is, we'll conduct the hypothesis testing with t statistic using students t distribution, and we'll assume that population variance is not known to us. Also, we'll see that t statistic is more effective when the sample sizes are small, and for t test, degrees of freedom is an important property or an important feature that needs to be computed to perform t-test. So to start with, first we'll start with two-tailed test, and for that we'll design our t-test like this. We'll run the t-test command. We'll provide the argument pre-sample variable pre. We'll specify the mean as 4.5 because we are assuming or we are trying to test whether population mean is same as 4.5 or different than that. We'll provide the alternative, which is two-sided. That means we are conducting a two-tailed test. We'll provide the confidence level as 0.95. That means significance level of 5%. Also, please notice we have not provided any argument regarding the standard deviation of population, because assumption here is that standard deviation of population is not known to us. Now we'll try to run this command, and once we run this command, notice the t statistic, which is minus 5.8733. This is the t statistic for this test, and if we are doing the critical value analysis, we need to generate the critical value of t statistic. For that, we would require the degrees of freedom, which can be easily computed as length of sample size minus 1. So this is my degrees of freedom. Once I have my degrees of freedom, I can generate the t statistic, the critical value corresponding to 5% level of significance using this qt command. I'll write qt, and probability value, which is significance level, is given as 0.05 divided by 2. Why I'm using 2.5% or 0.05 divided by 2 is simply because it is a two-tailed test. So we are conducting the hypothesis test that 4.5 is different from the population mean. That means the population mean can be either more as well as less. So it's a two-tailed test, and that is why we are using 0.05 divided by 2 as our significance level. We also provide the degrees of freedom to our argument, and then we specify lower dot tail as true. Why we are doing this? As we discussed earlier, the t value appears to be negative, and therefore it seems it is more appropriate if we examine the t values on the lower side. That is, we examine the critical values on the lower side. So we generate this critical value, which is minus 2.00, as compared to our t value from this test, which is minus 5.8733. It appears to be quite small, and therefore we can safely reject the hypothesis that population mean is 4.5. Now, a more simpler way would have been to simply look at the p-value of this test, which is very small, close to 0, and therefore with a lot of significance we can easily reject the hypothesis directly looking at this p-value and say that our population mean is not same as 4.5. So with this, we have implemented the t-test in this video, and in the next video we'll try to see whether we can find if the mean is more than 4.5 or less than 4.5 by conducting single tail tests. We'll also examine what are the critical differences while we are conducting t statistic and z test statistic related hypothesis testing. In the previous video, we conducted the two-tailed hypothesis testing using t-test statistics. Now let us compare our results across z-test statistic and t-test statistic. And for that, we'll start with the sample size of 100. Let us start with the sample size of 100. We extract that from our original data of 1000 observations. Now that we have extracted our sample, we'll start with the hypothesis testing using z-test statistics. Let's look at the result. A very low p-value, which is almost equal to 0, is obtained. Let us conduct the same test using t-test statistic. Two-tailed test. Again, a very low p-value, which is almost close to 0. So not much difference, although still it is higher, but still we can consider them to be almost similar level of significance. So now we'll decrease our number of observations. As of now, it appears that both of these tests are giving almost similar level of significance, which is very close to 0. But now let us take 10 observations, a sample comprising 10 observations. We'll extract that sample from our original data again. Let us first consider the two-tailed test with z-test statistic. It is 0.006. Now again, we'll perform the same test with t-test statistic, and the value is much larger. Notice the p-value, it is much larger. It is 0.0195 as compared to a p-value of 0.006 with z statistic. What do we infer from here? Please notice, when the sample sizes are low, the p-value is higher with t statistic and it indicates a lower significance. That means t-test statistic instills a more sense of reality when you have low number of observations and also you do not know the population variance. Then it is more proper and more appropriate to have more evidence in favor of rejecting the null. That means if you want to reject the null, you would probably want to have more evidence when your sample sizes are much lower and population variance is also unknown. And that is what is facilitated by t-statistic hypothesis testing. Given the nature of students t distribution, it is much fatter around the tails and the peak is lower at the mean, closer to mean. It indicates that this is more closer to reality. That means when observations are low, number of observations are smaller, and also we do not know the variance and standard deviation of our population, then it is better to have slightly more evidence, relatively higher evidence, to reject the null. And that is what is precisely achieved with the t-test statistics. In case when we have large number of observations, then as we have noticed already, the inferences and the significance of tests is quite similar between whether you use t statistics or z statistics hypothesis testing. So now we'll move to single tail test and we'll try to establish whether the population has a mean of more than 4.5 or less than 4.5. So in this, we'll conduct the t-test to see whether population mean is more than 4.5 or less. So first, let us see if it is more. Although we already have some intuition looking at the previous z values and t values that it is lower than 4.5, but still we'll design our test. So we'll give the sample pre mu value of 4.5, alternative argument as greater to see if the mean is greater than 4.5. We'll establish the confidence level as 0.95, that means a significance level of 0.05. Let us run this. Notice a p-value of 0.99, which again indicates that our test is giving slightly spurious results. Why so? Because already we know that our population mean or the sample mean also is much lower than 4.5. So that means this test is rather spurious, and we'll focus on the lower tail test. That means negative side of the statistic on tail. So we'll conduct the t-test, use our pre-sample as we did earlier. We'll put mu equal to 4.5, alternative as less, and confidence level as again 0.95. Please notice here we are not giving the standard deviation or variance argument. Why? Because assumption is that variance of the population is not known to us. So from here we can compute the relevant t statistic, which is coming as minus 2.8363. Now if you want to conduct the critical value analysis, you can simply generate the critical t value here using the qt function. You can use qt and specify the p value of 0.05, that is 5%. Please note we are not using 2.5%. Why? Because it is a single tail test, so we are looking at only one tail, the lower tail, and therefore we are using the argument p as 5%. We also need to supply degrees of freedom, but before that we'll put the sample size as 50. So we'll put the sample size as 50 and compute our degrees of freedom as length of sample size -1, and then we'll run this. We'll give the degrees of freedom as DOF, and also we'll put the argument lower tail as T. Why? Because we are looking at the lower side of the tail, the negative side of the T statistics. So we can easily compute our relevant T statistics as -1.67. Notice that the magnitude of this critical value is much lower as compared to the test statistic t value that we computed earlier, which is -2.8363. That means we can reject the null with a reasonable amount of confidence. And also, even without doing this critical value analysis, we could have directly looked at p value as well, which suggests that the significance level of this test is very high. So with a lot of confidence, we can reject the null and say that mean is less than 4.5. That is pre-sample mean, before the training and development mean observations, the sample mean, and the inference that we are making about the population, that population mean is less than 4.5. That is what we can infer from here. Now again, we would like to again check whether changing the sample affects the level of significance or not. So let us do this testing with 10 observations only. So let us do this testing with 10 observations, and this time we'll only run the single tail test, that is on the lower side, which is this. So we'll run this lower tail test, first z test. Notice the p value 0.001. Now let us run the same test with our lower tail on the for the t test statistic, and notice the p value is much higher, indicating a lower level of significance. So this again confirms the argument that we already made, that in case of t-test statistic, when you have lower number of observations and also you have made the assumption that you do not know the population variance, the level of significance of the test is lower. That means you need a larger amount of evidence to reject the null and be sure about your inference. So with this, we have understood the t-test statistics and z-test statistics, the critical difference between them, and we have already seen how to infer the population mean statistic using the sample data from t-test statistics and z-test statistics using hypothesis testing. In the previous video, we have examined the pre-sample data, that is before training and development program. In this video, we'll examine the post-sample data. We'll examine the post-sample data. We'll use similar Z and t-test statistics to conduct hypothesis tests, and we'll examine the impact of training and development. We'll use p-values to make inferences, and first we'll start with the z-test statistics hypothesis testing, and then we'll move on to t-test statistics. So first we'll start with the post-sample data with z statistic. So similar argument, we'll use z dot test. We'll supply our post data, which is the post sample data extracted from our previous 1000 observations. So we'll just extract the data, 50 observations we'll extract. So we'll extract the 50 observations, and then we'll put a mean of 4.5. Alternative argument we can set as two-sided. So first we'll start with two-sided. That means whether the post sample data has a mean of 4.5 or it is different than that. We'll again set our confidence level as 0.95, which means significance level of 0.05. Please notice, since we are conducting z-test statistic hypothesis, we need to supply the variance of population with this sigma dot x, which is same as standard deviation of original population, which is data dollar post. Here we are assuming that original 1000 observations that we had is like a population data from which we have extracted the sample. So this is our z-test statistic. Now let us compute the z statistic. It is 5.0742. In case we want to do critical value analysis, we can simply provide the argument q norm and supply the p-value, which is 0.05 divided by 2, because it is a two-tailed test, so we need to supply 2.5% as discussed earlier. Then we'll supply the lower dot tail as f. Please notice that the z value is positive here. In fact, it's particularly large, and therefore it would be better if we look at that upper tail, that is the positive side of the tail, the critical value corresponding to the upper tail. So we'll generate that. The value is 1.96. Now let us compare this 1.96 critical value with the test z value, which is 5.07, which is considerably large, which indicates that we can reject the null with a lot of confidence, and that means that the population mean is different from 4.5. It is not equal to 4.5, and without going to the critical value, even we can infer that from the p-value as well, where p-value is very small, indicating a very high amount of significance and a lot of confidence at which we can reject the null. Now let's conduct single side test, which is z-test on the positive side, that mean is more than 4.5, and for that again we'll supply the sample post. We'll put the mu value equal to 4.5, and alternative this time is greater. That means we are checking whether the mean is more than 4.5, population mean is more than 4.5 or not. Again we'll supply the confidence level as 0.95, and we'll supply the sigma dot x argument, which is the standard deviation of our population, which is data dollar post. Now when I run this command, notice the z value is 5.0742, and it clearly rejects the null, that is the true population mean is greater than 4.5, a very strong result which suggests that the mean is greater than 4.5. Now we can very well check that as well. We are not doing the lower side of the test because it is quite obvious here, given the z statistic and our previous hypothesis test, that It is obviously more than 4.5, so we are not doing the lower tail test. Let's look at the mean of population. So that is data dollar post, and it appears that indeed the mean of population, in this case the population would be the original 1000 observations, is much larger than the 4.5 value. This is also an early indication that indeed there is some impact of training and development on the population, what we have inferred from the sample statistic. So with this, we have understood the hypothesis testing on post data using z-test statistic, and now we'll conduct the t-test statistic hypothesis testing on our data. Now that we have examined the pre and post samples separately using simple single sample hypothesis testing, in this video we'll analyze and compare the pre and post samples together using two sample tests. So we'll analyze pre and post samples together using two sample tests. First, let us start with simple z-test statistics. So we'll start with z-test hypothesis testing. As we have already seen, we'll use z.test command and we'll supply our pre and post arguments, alternative as two-sided. We'll set the confidence level at 95%. Now in this case, we need to supply the population standard deviation for both the pre and post samples, because we are conducting z-test, assuming that population variances for both the samples are known. We'll supply them sigma dot x. So first we'll supply the population variance of the pre-sample. Then we'll supply sigma dot y, and we'll supply the population variance of post sample. So now that we have supplied the relevant arguments, let us try to see what we can infer about this z statistics. Notice, and we'll focus on the p-value and z statistic here. Notice this p-value clearly indicates that there is a significant difference pre and post. Notice the mean of pre is 3.99, the mean of post is 4.90, and their difference, the confidence interval is minus 1.14 to minus 0.69. Zero does not lie in this, so there's no zero in this interval. And given the p-value, the significance level of this p-value, it clearly indicates that the difference in their mean is not zero, and obviously the post value of mean is higher as compared to pre-value. So this is an early indication that clearly we can reject the null that their means are equal, and early results suggest that post is higher than pre. Now we'll do some more analysis on this, and first we'll start with the one-tail test. So we'll apply our z-test for pre and post. We'll supply the alternative argument as greater. So it will be a one-tail test. Again, the confidence level is 0.95, and we'll set our standard deviations argument to, as we did earlier, we can supply the population standard deviations. Let us run this test. Notice the difference is negative, that is pre minus post is negative, and therefore the p-value is 1, which means this test is spurious. That means clearly the post values are more than pre, and therefore this test becomes spurious. So we'll focus on the other side of the tail, the positive side. So let us conduct that test using z-test statistic. This test was very simply spurious because the pre values were clearly lower than post. So the hypothesis that pre is greater than post was clearly not rejected. So we'll conduct this pre-post alternative. We'll supply the argument less, that means pre is less than post. And now we'll design our hypothesis with confidence level of 0.95, and we'll supply the population variances. If I run this, we are testing one tail test and checking whether pre is less than post. So the null hypothesis is it is not less than post, and the alternate hypothesis is that pre is less than post, and clearly it is rejected. It appears that the hypothesis that this pre is not less than post is rejected with a lot of confidence. The p value is much lower and a very high level of significance is associated with this. That means we can very easily say that post is greater than pre. We can also confirm this by running this population difference. So we can directly check the differences between the population from pre and post, and it should not surprise us to find that indeed post is more than pre. That means the difference is negative. So pre is lesser than post by a difference of minus 0.98. So which also confirms that our inference drawn from the sample is efficient. Now that we have conducted the z-test of differences between population means of pre and post sample data, we'll move towards t-statistic test. That means we'll design our hypothesis using t-statistics. In this video, we'll conduct the hypothesis testing using t-test statistics. We'll conduct two sample t-test hypothesis, testing and compare the means of pre and post sample and make inferences about the data. First, we'll conduct the two-tail test, and then we'll design single-tail test to check if there is indeed an increase in employee satisfaction due to training and development programs. So we'll conduct the t-test, and t-tests are done when population variances are not known and sample sizes are small. So we'll start our simple t.test command. First we'll supply the pre-sample, then post, then we'll set the alternative argument as two-sided. So here we are simply comparing the pre and post means. We'll set the confidence level as 0.95. Please note we are not providing here with the standard deviation or variance of the population as we did earlier with the Z statistic, because the assumption here is that those variances are unknown. So we'll run this test and notice the t value of minus 8.7441. And also please notice the p value, which clearly indicates that with a lot of confidence we can reject the null and say that the mean of pre and post sample are not same. So we can make that inference about the population. Also, there is some evidence to suggest that mean of pre sample, which is around 3.99, and mean of post sample, which is around 4.90, are quite different. However, we'll have more to say about that in subsequent tests. So let us start with the single tail test. In the single tail test, let us first compare the greater. Alternative argument is greater. That means we are saying pre is greater than post. Although if we look at our t statistic that we computed earlier, it would suggest that pre is indeed lower than post, and therefore this hypothesis is slightly spurious. But still, we'll try and test that. We'll provide the confidence level of 95% and let us run. Look at the p value. It is equal to 1, which again substantiate that this hypothesis was sort of spurious because we already knew that pre is much lower than post. But to check the statistical significance of that and prepare our hypothesis design around it, we'll rather use the upper tail. That means we'll use the lesser argument. We'll put our alternative as less. That means post is greater than pre. So post minus pre is on the positive side and pre minus post is on the negative side. So we'll set the confidence level as 95% and let us run this. Notice the t value is negative and very significant, which again conforms to our original hypothesis that pre is much lower than post, or we can say that significantly lower than post. So this result is statistically significant, which is also confirmed by a very low p value, which indicates a very high level of significance. That means we can reject the null with a lot of confidence and we can make the inference that pre is significantly lower than post. Overall, from these results, we can easily infer that there is substantial impact of training and development activity. That means the employee satisfaction before training and development, which we sampled in our pre-data, and then post training and development, there is a considerable increase which is statistically significant as well. That is what we infer about the population. Now let us check what is happening in the population itself. So we'll put mean of, we'll take the differences between post and pre and let us see if it is indeed large. We are directly working with population now, so we can see that the difference is indeed quite large. It is 0.98, which suggests that the inferences that we made about the population are indeed valid and they hold with the population. Let us recollect the business case with Zio Limited. The firm considered those with a survey response of less than 4.5 as detractors and assigned a value of 0. Those with a score of more than 4.5 were considered promoters and were assigned a value of 1. The firm wants to focus on those detractors with the 0 score, and it wants to design customized programs suitable to these detractors. Now, in order to perform this analysis, we'll model the data and design hypothesis tests using binomial distribution. So first, we'll start with examining pre-sample data with single sample tests. First, we'll create our pre-bino variable. As we did earlier, we'll run this if-else code. We'll assign a value of 0 to those with a score of less than 4.5 and others 1. Now one can create the proportional test, prop.test function. We can use that. We'll use the summation of pre-bino, that means all those with a score of 1, and we'll provide the sample size, which is 50. We'll provide the confidence level, which is 0.95, that means 5% of significance, and we'll provide the alternative argument as two-sided. If I run this function, essentially I'm testing a hypothesis that whether it is a score of 0 or individual score of 1, that means there are two binary scores, 0 or 1, there's equal probability of any individual having these scores. First, we can perform critical value analysis using chi-square, critical chi-square values. It's quite easy. We can provide the confidence level, that is 95%, and score of 1. Since we are looking at the upper side of the tail, higher side of the tail, we are providing the confidence interval. If we were looking at the lower side of the tail, we would have provided the significance level, that is 0.05. So if I run this, I find a critical value of 3.84, which is much lower than the 19.22. Or in another way, we can also look at the p-value and infer the same. The p-value is quite low, in fact very close to 0. That means with a very high significance level, we can reject the null and say that any individual having a score of 0 and 1, if we pick any individual randomly having a score of 0 and 1, does not seem to have 50% probability. So that means there is a bias. The probability that individual have a score of 0 or 1, or he's a detractor or promoter, is not same. Now let us examine this in detail. We need to check whether there is a higher probability for promoter or detractor. So to conduct that kind of test, we need to design one tail test, and therefore first we'll put the argument as greater. That means we are checking whether those with a score of 1 have a higher probability than those with a score of 0, and let's run this command and notice the p-value is 1, which indicates that this hypothesis was indeed spurious. Why? Because in our previous test itself, we could see the sample estimate of 0.18 and sample interval as 0.09 to 0.319, which is lower than 50%, 0.5, which already indicated to us itself that those with a score of 1 have a lower probability than 50%. So in this hypothesis, where we are hypothesizing that null is that their probability is 50% and alternative is that probability is greater than 50%, is spurious. So we'll modify our hypothesis and we'll look at the other tail. That means other arguments remaining the same. That is, we'll supply the pre-bino sum of pre-bino variable, 50 sample size, confidence level as 95%, but the alternative argument would be less. That means the probability that an individual has score of 1 is less than 50%. That is my alternate. My null is that the probability of an individual having score of 1 is 50%. The alternative, it is less than 50%. So this is my alternative hypothesis. If I run this command, it is indeed the case. That means my chi-square value clearly indicates and p-value indicates that with a lot of significance we can say that getting a score of 1, that means if I pick any individual randomly, the chances that his score is 1 is less than 50%. Now I can also apply the chi-square test here. How? So I can simply put q chi-square. Since it is a single tail test, I'll put the argument as 0.90 comma 1, and I'll have the, it is 2.70, which is again much less than 19.22. So with a lot of confidence I can say that it is less than 1. Again, if it was two tail test I would have provided 95. Since it is single tail test I am considering 0.90. Now we will examine the same for our post bino variable. So till now we have examined the pre-bino variable and we have reached the conclusion that in the population, the probability that if an individual has a score of 1 or he's a promoter, it's much less than 50%. We can also check this as well. How do we check this? So we can use the population data, which is data dollar post. For population, we can create a new variable pre-bino population. We can assign a score of 0 if it is less than 4.5. We can assign a score of 1 if it is more than 4.5, and we have this population with score of 0 and 1. Now what we can do is we can divide this pre-bino population with the length of sample, which is 1000, and let's look at that. So we need to add the sum here. Once we assign the sum and divide by 1000, it's 25.5%. So in the population itself, the probability to observe an individual with a score of 1 is 25.5%, which is much less than 1. And this is what precisely we estimated from our sample hypothesis testing. With this, we found that in our pre-sample data, the probability to observe an individual with a score of 1, that is promoter, is much less than 50%. So now we'll examine our post-sample data and make inferences using binomial distribution. In this video, we'll analyze the post-sample data using binomial distribution. We'll conduct the hypothesis tests for proportions and make inferences similar to that we did for pre-sample data. We'll also examine the probability of an individual being detractor, that is a score of 0, or being promoter, that is a score of 1, if it is same or different. And also we'll examine if there is any impact of training and development on employee being detractor or promoter. So we'll start with post sample data. We'll model it using binomial distribution. So first we need to create our post bino variable as we did for pre-sample pre-bino variable. So we'll create this post bino variable using the same if else argument, and we'll assign a score of 0 if it is less than 4.5 and 1 otherwise. Now we'll conduct our prop.test and we'll supply the argument sum of pro by post bino, which is those individuals with a score of 1. Summation will be the sum of all those ones and sample size 50. We'll provide the confidence level as 95%, remains the same as earlier, and we'll provide our alternative hypothesis, which is two-sided. That means the probability if it is 0 or 1 is equal to 50%. It is null, and whether it is more or less, that will be our alternate hypothesis. So if I run this argument, I get a chi-square value of 16.82 and a sample statistic of 0.8. Sample estimate suggests that the probability of having a score of 1 may be higher than 0. We'll again look at the critical value. We can examine the critical chi-square value by supplying 95% confidence and degrees of freedom as 1. We can run this and we can see the chi-square is again 3.84, which is much less as compared to the test statistic chi-square, which is 16.82. We can also infer the same from our p-value, that is 4.11 e to the power minus 5, which suggests that with a lot of significance we can reject the null. That means finding the probability that an individual score of 0 or 1 is not 50%. It is significantly different. And some indication, some intuition is also provided that it is more than 0.5, which we can gauge from the interval. Confidence interval start from 0.658 at the lower side and 0.894 at the higher side. And the sample estimate is 0.8. So there are some evidence suggesting that the population mean, the mean value may be higher than 0.5. So with this, we move towards more precise test, one-tail test, to establish whether this probability is more than 50% or less than 50% of finding an individual with 0 or 1 score. So we'll again conduct our prob.test and some post bino variable summation. 50 is the sample size and confidence level is 95%. Let's give the alternate hypothesis as greater. Since we already have that intuition that the probability of finding the individual as 1 may be higher, so we'll examine that hypothesis. And it is indeed the case, it seems, that chi-square value is 16.82 and p-value, p-value is much lower. That means a very high level of significance. So when we are rejecting the null, that observing an individual with a score of 0 or 1 has equal probability, we are rejecting it with a lot of confidence and a lot of significance. That means the probability of identifying an individual with a value of 0 or 1 in population is indeed not same, and probability of having 1 is much greater with a sample estimate of 0.8. So we can also conduct the opposite hypothesis, although it will be spurious because we have already seen that the probability of having an individual with a score of 1 is much higher, but still we'll conduct the opposite hypothesis. Same arguments, we'll use sample size as 50, confidence interval as 95%, and alternative is less, which means that we are saying that identifying an individual with a score of 1 has less probability, that means less than 50% probability, than identifying finding an individual with a score of 0. So if I run this hypothesis, please notice the p-value is 1, which clearly indicates that this was a spurious hypothesis. We already knew that somebody with a score of 1 will have a higher probability than somebody with a score of 0. This we can also establish by directly looking at the population. How do we do that? So first we'll construct the post bino variable for our population. So we assign a score of 0 to those observations that are less than 4.5 and otherwise 1. So now I can see in the population itself what is the proportion of those individuals having a score of 1. Let us see that. And if I run this, it's 75%, which clearly indicates that the individual having a score of 1 are almost 75% in the entire population. This also is a very clear signal that there is indeed some impact of training and development, and therefore in the pre-sample analysis of proportions using binomial distribution, we found that individuals with a score of 1 have had much lower probability, much less than 50% pre-sample, and after training and development that probability has increased considerably. So there is a significantly higher probability than more than 50% that an individual will have a score of 1. That means employee satisfaction has improved after training and development programs. So this is what we can infer from these single sample tests taking pre and post variables separately. In the next set of videos, we'll examine this using two sample analysis, two sample hypothesis testing by using pre and post samples together. In this video, we'll conduct two sample tests of population proportion using binomial distribution. We'll model the data and we'll compare the proportion of detractors and promoters in the pre and post sample. and then we'll make inferences about the population proportion pre and post training and development programs, and we'll try to find whether promoters have increased after training and development program. So we'll conduct two sample tests of population proportion using normal distribution, and to start with we'll again use that prop.test command. We'll now supply not one sample but two samples very easily. So first we'll provide post bino, and then we'll provide pre bino, next is sample size, which is 50 for both the samples. Then we have confidence interval as 95%, and we'll provide alternative hypothesis as two-sided. So we are providing alternate hypothesis as two-sided. So essentially we are testing here that the proportion of detractors and promoters is same across both the populations using the data from sample. So if I run this command, please notice that the p-value is very small. That means the level of significance is very high when we are rejecting this null. So with a lot of confidence and significance level, we can say that the proportion of promoters and detractors is not same across both the samples. Now, whether promoters have increased after the training and development program, that we'll try to identify using one tail test. So we can conduct them very easily using the same function again. Again, we'll use the similar set of commands, some post bino, and we can provide the sum for pre bino. Then we can also supply the sample size as 50-50 for both the samples. We can supply the confidence level as 95%, and then we can provide the alternate hypothesis, which is greater. So here we are testing whether the proportion of promoters in post sample have increased from pre sample. Let us test that. Please notice that the chi-square value and corresponding p-value indicate the p-value is in fact quite low, indicating that the proportion of promoters in post sample is much higher as compared to post sample. So we are able to reject the null with a lot of confidence and a very high level of significance that the proportion of promoters is considerably higher in the post sample as compared to the pre sample. Although not needed, we can also test the other hypothesis, that is of less. That means the promoters are less in post sample as compared to pre sample, and we can test that hypothesis very easily. Look at this, the p-value is 1, which indicates that this hypothesis was spurious. We already knew that promoters in post sample are more as compared to pre sample, so therefore the other way around, that is promoters are more in pre sample as compared to post sample, that hypothesis is spurious. We cannot reject the null as we have already discussed. So in conclusion, we can say with this hypothesis testing exercise that because of training and development program, there is a very statistically significant increase in promoters after the training development program as compared to before training and development program.